Hello everyone, I am Alba Fernández Izquierdo, and in this part of the tutorial I will present the Ontology Languages. In this tutorial we will be talking about ontology languages defined by the W3C, which are focused on knowledge representation and reasoning capabilities on the web. In this slide you can see the Semantic Web stack, which illustrates the hierarchies of the languages, where each layer exploits and uses the capabilities of the layers below. The idea behind this Semantic Web stack is to propose a data model and on top of it the semantics, the ontologies, that I can use to represent such data. Related to these ontologies, we also have querying languages, like Sparkle, that allows us to query data represented using ontologies. In this tutorial, we will focus on the language for data interchange, RDF, the language for defining taxonomies, RDFIS, and the language for ontologies, OWL. So the first language is RDF. RDF is the basis for having linked data on the web. It's a W3C recommendation that defines the conceptual data model and also the syntax to serialize that data model and the semantics, the logical formalism to understand and reason over the data. RDF was designed to support interoperability on the web, so that the machines are able to exchange data. In this case, the end user of RDF is the machine. So in order to be machine readable, RDF has different serialization, which are the ones that are listed in the slide. All the serialization are standards, and they are focused on several aspects. For example, Turtle is designed to be a more user-friendly serialization, while JSON-LD is more oriented to support the developers. The data model in RDF is very simple. The RDF data model is based on RDF triples, which consists of a subject, a predicate, and an object. These triples allows us to define sentences. For example, a thermostat offers a thermostat service, or that thermostat is located in Madrid. A set of triples with some concept in common generates an RDF graph, as the one that is shown in the slide. In this RDF graph, the common concept is a thermostat, which measures on temperature, is located in Madrid, and also offers a thermostat service. Since RDF is grounded on the web architecture, the resources are identified through URIs. For example, the subject thermostat that I mentioned in the previous slide need to be associated with a URI, as the one that is in the slide. This also happens with the predicates and the objects, for example with measures and temperature. All these subject, predicates and object need to be associated, need to be identified through a URI. The inference in RDF is very simple. It only includes two rules. The second rule, for example, states that if we have a triple, a resource appears as a predicate in the triple, then the resource is classified as an RDF property. For example, if we have a subject A, a predicate P, and an object 1, 2, 3, then P is going to be classified as an RDF property. Then we have RDF Schema or RDFIS. RDF Schema allows us to represent more complex ontologies. If we compare RDF and RDF Schema, we first have RDF to represent the data, and then we have RDFIS, RDF Schema, to represent the schema of that data. So RDF Schema extends RDF. RDF Schema allows us describing classes and individuals. For example, it allows us to define Madrid as an instance of a city. It also allows us to define constraints on the use of properties. For example, it allows us to define domain and range of the property. In the slide, you can see a property makes measurements that defines as a domain a device, and as the range a measurement. And also RDF Schema allows us to define hierarchies, property hierarchies and class hierarchies. For example, in the slide you can see that a sensor and an actuator can be defined as subclasses of devices. The inference in RDFIS is stronger in comparison with RDF. The table in the slide shows the 13 rules in RDFS. For example, the rule 11 defines the transitivity. In this rule states that if we have a class A, which is a class of class B, and also have a class B that is a class of class C, then class A is also going to be a subclass of class C. Then we have OWL. OWL is designed also to be part of the schema. It extends RDFS so that we can represent much more complex ontologies. OWL still uses RDF data because we have to keep in mind that OWL is built on top of RDF. The OWL language is a W3C recommendation since 2004, and the latest version of OWL is OWL 2, which is a W3C recommendation since 2009. As I mentioned before, OWL is built on top of RDF and extends RDFS. OWL allows us describing the semantics of information in a machine-processable way, since it's based on RDF data. Also, OWL is grounded on description logics, which allows us to represent much more information. OWL allows us to describe a domain based on its concepts with classes, roles with relationships, and individuals with instances. Also, OWL has more capabilities, for example, the open world assumption, which refers to the fact that we cannot assume that we have all the information. And this idea is translated into the definition of ontologies. OWL includes 3 different species of OWL, different sublanguages. These different sublanguages have different expressivity. The more expressive one is OWL full, which has maximum expressiveness and syntactic freedom of RDF, but with no computational guarantees. Then we have OWL-DL, which also has maximum expressiveness, but retaining computational completeness. And finally, we have OWL-Lite, for users that only want hierarchies and simple restrictions. This table shows the summary of the vocabulary defined in OWL. As mentioned before, OWL extends RDFS so that we can develop more complex ontology. New restrictions included in the OWL vocabulary are, for example, the intersection of classes, union of classes, negation, also universal restriction and existential restriction, or cardinalities, including maximum cardinality, minimum cardinality, and exact cardinality. I also want to mention that OWL allows us to define restriction not only related to the model, but also related to the data. For example, the one-of constructor allows us to define an enumerated range of data values in the ontology. This table shows an overview of the most common restriction in the OWL language. However, you can find more restrictions in the list, in the reference specification, and in the quick reference guide. And the link to this specification is in the slide. The reasoning in OWL is stronger than in RDFS. As mentioned before, a reasoner generates inferred axioms from asserted ones. OWL is defined to offer a sound and complete reasoning. However, if you use OWL full constructs, this may lead to an incomplete or inefficient reasoning. If you use OWL-DL or OWL-Lite, you will have no problems in terms of efficiency in reasoning. Reasoners have evolved and improved over the years. However, in order to avoid some problems in some scenarios, 3 different profiles are defined. These profiles limit the subset of restrictions used in the OWL language in order to support specific use cases. These three profiles are OWL2EL, OWL2QL, and OWL2RL. So the first profile, OWL2EL, can be used if you have ontologies with very large number of classes and properties. The second profile, OWL2QL, can be used if you have to express certain conceptual models, for example, UML and ER, or if you have applications that use very large volumes of instance data. And finally, the third profile is OWL2RL, that can be used if you have rule-based technologies. In this last section, I'm going to describe how to query over RDF. So it's possible to query RDF data the same way we can query a relational database. In a relational database, we need to use SQL queries. If we have RDF data, we have to use Sparkle queries. The execution of Sparkle queries is supported by the most relevant APIs and triple stores used in semantic web technologies. For example, the APIs Jena or Sesame support these Sparkle queries, and also the triple stores Virtuoso, Stardog, or Fuseki. So as an example of querying over RDF, we can have the sample RDF graph that is in the slide. This sample RDF graph includes an instance, thermostat 001, that measures a temperature and that has a serial number. The code in the right side of the slide shows the RDF data using turtle syntax that represent this RDF graph. So if we have this RDF graph, we can execute queries. For example, which are the devices that measures temperature? So to solve this query, we need to identify the concept that measures temperature in the sample RDF graph. The code in the right side of the slide shows the Sparkle query that solves this query in the RDF graph. The answer to this query will be thermostat 001, which is the device that measures the temperature in the sample RDF graph. And this was the tutorial on ontology languages. Thank you very much.